All right, this is Physics 101, Chapter 5A lecture. Let's see if I end up covering. And this will be on circular motion and friction on a turn. So I'll do another lecture later on. So it'll be on circular motion, the concept of circular motion, friction on a turn. Next part will be a lecture on Newton's law of gravitation and orbital motion of the planets. So this first one, we'll just get through this part first, and then I'll do the next lecture. So, all right. What we have here, when we have linear acceleration, so when we go from v naught to v in a distance x, all right, then the acceleration is, well, we have the expression is v squared is v naught squared plus 2ax, all right? So in the case here, we start from 0 to 20 meters per second, and we do x is 40 meters. What's the acceleration? It would be 20 squared equals 0 plus 2 times a times 40. All right, so that would be 400 equals 80 times a. So a would be 5 meters per second squared. All right, so this is linear acceleration. We're going in one direction, so that's the case there. Now, if we have constant velocity, all right, we have start from 20 meters per second, and we go 20 meters per second, right? In a straight line, our change in velocity is 0, so the acceleration is 0. So when we go a constant velocity, so we have constant speed in a given direction, change velocity is 0, acceleration is 0. All right, so that's what we've done for the first few chapters. Now what we're going to do is something a little different, is what happens if we are going at constant speed but changing our direction. And the simplest example of that, so I'll leave this up for a minute. So we have this constant speed in a given direction, straight direction, acceleration is 0. What if I go in a circle, all right, with some v is 20 meters per second, and I go in a circle of some radius r. Now you've seen that when you go merry-go-rounds or anything, even though you're going at constant speed, you are feeling acceleration because you're feeling like you're being pulled out. This feeling of being pulled out is centripetal acceleration, and that's a result of being pulled in, what we call centripetal acceleration, ACC, right? AC, so this is what we call centripetal. And you're being pulled in a circle, you're being pulled to go in a circle constant speed. The acceleration, centripetal acceleration, is given by v squared over r. Okay? Now 20 meters per second is about 66 miles per hour. So that's a very high speed. So say we're doing that in a circle of, say, 20 meters. Which is pretty narrow. It's only about 60 feet. No, that's not 66 miles per hour. That's about, never mind. That's about 45 miles per hour. All right. Yeah, because 1 meter per second is about 2.24 miles per hour. All right. So, all right. So if we're doing that, go in a circle into radius, what would be the centripetal acceleration? Well, the centripetal acceleration would be 20 squared over 20 AC, which would be 400 over 20, would be 20 meters per second squared, which is about 2g. So that's actually a very strong acceleration. It would be very hard to feel extremely uncomfortable. So like centrifuges do this sort of thing. So you're moving at a constant speed, but you are constantly changing your direction, and the definition of acceleration is a change of velocity. And if you're changing your direction, you're changing your velocity by moving in a circle. And that's what we call centripetal acceleration. Okay. So given this, so it's v squared over r. So related to this is we're going to talk about, going around one period, time for one period. So that's what we call the period. And we'll see this later on. And then the frequency is 1 over the period. So if you have a period, say, going this speed, well, we can figure out, if you're going 20 meters per second, the circumference here would be 2 pi r, would be 2 pi times 20. So that's about roughly 125 meters. And if we're doing that 20 meters per second, the period would be roughly 125 over 20, which is roughly 6 seconds, right? So you'd be going a circle once every 6 seconds. And then the frequency would be 1 over the period, so that's 1/6 what we call hertz. All right, we'll get into this more later when we do rotational motion in, I believe, chapter 8. All right, so that's some introduction to this there. All right, so we have centripetal acceleration is defined as v squared over r. This is the case. And then the period is the time it takes for it to go around one time. And the frequency is that. All right, so this case here, we're actually thinking about going in a circle, like you're driving in a circle, where it's horizontal. All right, in this case, we have no other forces acting on it except for that. Now, we can do some other things, and they have examples. We're not going to do this problem right now, maybe a little later. But you have a case of, you have a roller coaster that goes upside down. All right? Now, so you have it going in a vertical circle. Well, in that case, we have gravity acting on it also. So let's look at that for a moment. Okay. And what have we got there? Okay. In this case, if we're going a vertical circle and say a radius of, say, 10 meters, right? And you're in a vertical circle, so you're in a roller coaster that goes upside down, right? What are the forces acting on it as it turns? All right? Well, what you have is it's going at some speed. So the centripetal acceleration is going to be v squared over r. But at the same time, you're going to have gravity pulling down. Right? Acceleration of gravity is, minus 10 meters per second squared. Right? Now we're going to have gravities pulling down. Now what you're going to see, I'll give you an expression here. When this thing is going, at the bottom part, where you can see, in all cases, we have AC is v squared over r. AC is v squared over r. Assuming it's going at constant speed the whole time, based on that, what would be the net acceleration field on this thing? And a question might be, is given an idea of seeing like that, if it goes up, what would be minimum speed to stay on track? So let's look at this. All right. So what's going to happen is at the bottom, you're going to have this, and the easiest way to think of it is centrifugal force is trying to pull you out. So that's v squared over r. Plus you're going to have gravity pulling on it. So these are both going to be positive, and we're going to use G is approximately 10 meters per second squared. We're going to take the absolute value of it. So this would be at the bottom, plus, right? That would be the acceleration field. If you're at the top, it's going to be v squared over r minus g. Where g, again, we're using 10 meters per second squared. We take the absolute value. All right, so let's pick an example where it's going, v is 20 meters per second. Right, so it's going 20 meters per second. It's going to be, well, let's make it 10 meters per second. 10 meters per second, all right? Oh. Then at the bottom, it's going to be your total acceleration will be v squared over r, which is 10 squared, over 10 plus g, which is 10 plus 10 or 20 meters per second squared. I think I picked the wrong number here. At the top, it's going to be v squared over r, 10 squared over 10 minus 10, which turns out to be 0. So it turns out that's the minimum speed it is to do that. To solve this more exactly, all right, the minimum speed would be given by v squared over r minus g is 0, or V squared over R equals G. So depending on the situation, this is how you'd find the minimum velocity the minimum velocity or radius to maintain staying on the circle. So it would actually be going up, feel 2 G's here, and 0, 2 G's. And that's why if you're in a ride, you feel that if it's going upside down, you feel the sense of kind of like falling out of it. So that's acceleration in a centripetal direction. Okay. So that's part of section 5.2. All right, the last section I'll do today will be on curves and friction. And if you go back to friction, friction is mu m, frictional force is mu mg, where we have static and we have kinetic friction. So we go back to all right. So if we have a dry road, wet, very wet, coefficient of friction, static friction can be as high as 1, and the kinetic friction is roughly around point, right? Point, right? When it's very wet, it can be as low as 0.5, and then the kinetic is 0.3, right? Which means that if you start to slide, if you're not able to stay, your tires stay on the road, and you start to slide, then you will slide even more because the sliding friction, again, kinetic is always less than static friction. So this is the Greek letter mu. All right. So and that's the whole point of, say, anti-lock tires is when you start to skid, it lets the tires move a little bit so they can catch and then hopefully catch on. If you just go into a skid, then this is going to be less and you're really going to have problems. So as long as you can maintain static friction, then you're going to be okay. So let's do an example here. We have a road. Right? All right. Let's pick a road where R is, say 50 meters, so that's about 160 feet. And you're going at a speed of 45 miles per hour, 20 meters per second. Now what you're going to have here is you're going to have centrifugal force, like we just talked about, will be V squared. V squared over R. Now we talk about meters, so let's talk about M. Let's have one car is 1,000 kilograms, all right? So the frictional force, this centripetal force, Fc, will be mv squared over R, which would be 1,000 times 20 squared over 50. Now, if we're on a dry road, so if it's dry, And the frictional force pulling in is going to be mu mg, all right? So if it's dry, then the frictional force will be mu, which is 1, times 1,000, times 10. I'm going to use 10 meters per second for G. All right? That's 1, so that's 10,000 newtons. All right? So what do we have here? This will be, let's see, let's see, that's going to be 1,000 times 400 over 50, which is 8,000 newtons. And because this is less than that, as long as the frictional force is greater than the centripetal force, the car will stay on the road, right? Because the frictional force is not literally going to pull you in. What it'll do is maintain the resistance, so it'll counteract whatever the centripetal force is up to a limit of 10,000. On the other hand, if the centrifugal force is too strong, stronger than this, then what will happen is you'll go flying off the road, all right? And Newton's first law will take over right away, because if you start sliding, you just start going straight line, because kinetic friction is less than static friction. All right, so now this was a dry road. Let's do this now with a wet road, a very wet road. Same speed, and see what happens here. All right, you're going the same speed. So this is what we have for a dry road. All right, I'll leave that up. This is not going to be any different up here. Centripetal acceleration is still 8,000. But instead of mu F friction is 0.5 times 1,000 times G, 10, that's only 5,000 newtons. This is less than the centripetal acceleration. It'll slide off the road. You will slide off the road. So this kind of a turn, 45 miles per hour on a very wet road, you'll slide off the turn on an unbanked height. That's all we're going to do is unbanked, which is, not uncommon for roads. So that's why you got to pay attention to that, because once you start to slide, you're going to slide. Now keep in mind here, if we set this equal, all right, so what's the maximum you can do? All right, what's the maximum coefficient? Well, let's have it sliding. What is the maximum speed we can do? All right. So in this case, it slides. It's a wet road, it's going to slide. All right, let's change this now. All right. Maximum stays on road. The maximum speed, max speed is going to be when the centripetal acceleration equals the frictional force. Centripetal force equals the frictional force. So this will be mu mg is mv squared over r. Now notice we have an m on both sides, and it turns out mass makes no difference at all. It's the kind of tires, but the weight has nothing to do with it. This is one concept people have a hard time with. When they've got a big heavy truck, well, it'll stay on the road. The problem is a big heavy truck has a lot of mass with it, so the centrifugal force trying to pull it out is going to be a lot more too. So this is the case here. So we can figure out the speed, maximum speed will be R times mu G is V squared. So V would be equal to mu RG. So this is a maximum speed. And that'll be given by square root of, what do we have here, 50 times 0.5 times 10, which is 250. Square root of 250, which is, let's see, 14, no, 15, 16. So that's the math, but roughly 16 meters per second. All right. So when it's wet, max V is about 16 meters per second, or roughly 40 miles per hour. No, not even that, about 37. Let's say 35 miles per hour. So that's what happens when it's wet, all right? So that's how we have the expression. So frictional force is given by mu mg. Centripetal acceleration force is given by mv squared over r. And as long as frictional force is greater than that, it'll stay on the road. The maximum is when they're equal. And also turns out that the mass has absolutely nothing to do with the conditions, all right? So that is the first part of chapter 5. I'll do the lecture on gravity and orbits of the planets next time. So have a good day.